Okay, we'll do the week 5 cheat, the settlement cheat, using Hooke's law. Through this, I'll flick back the stress analysis and do some revision on what Hooke's law means, and I'll try and put it in simple terms, typical Bolton. I'll try and make it simple so we can understand it. May not be 100% technically correct, but hopefully you'll understand what's going on. So what do we know? We know it's a raft. It's, put it on a pen. It's 10 metres by 20 metres. Load is 16,000 kilonewtons. It's 2 metres deep. So they've excavated 2 metres to pour this foundation. It's a stiff clay. And it's 12 metres thick, the layer of clay, and water table is at the surface. Surface. Some properties of the clay. EU undrained modulus is 12 meganewtons per square metre. Effective modulus equals 10 meganewtons per square metre. Effective Poisson's ratio equals 0.25, and gamma bulk density is unit weight is 20.5 kilonewtons per cubic metre. We've also been given this other thing called, I'll write it in here, Scampton mu value equals 0.5, and we'll deal with that right at the end. The other thing they've given is they've already done the stress distribution to the under the centre of the raft at the midpoint of the layer. Of course, it's linear elastic. We can just use the average, the midpoint, and apply it over the depth. Hopefully that makes sense. So sigma V equals 0.7 Q, and Q is just the load from above here. Well, Q is the contact pressure. We'll distribute that over an area. And that's the change in vertical stress. The change in horizontal stress equals 0.3 Q. That's total stress. If you remember in the lecture, I said if you're doing immediate settlement, total stress, assume that Poisson's ratio equals 0.5, and the change in horizontal stress is 0.1 Q. That's when we're working in effective, and the effective Poisson's ratio given above is 0.25. So we'll leave it at that, and then we'll come back and we'll do some calculations, initial calculations. Okay, so we know we'll calculate Q first, the contract pressure, or the increase in pressure. So we've got 16,000 kilonewtons divided by 200 square metres, the area of the raft. Pressure equals force on area, simple, equals 80 kPa. And we've got the effective overburden pressure, not the effective, the total overburden pressure at the footing base. That's the stuff we're going to remove to excavate, to put this foot raft in. And that equals 2 metres by 20.5 kilonewtons per cubic metre, equals 41 kilopascals. few questions asked about this in the tute. All I want you to think about is the ground surface level. We've got a little bit of soil here, 2 metres below the surface. It's experiencing 41 kilopascals before anything happens. So then we excavate this 2 metre deep area and we add this 80 kilopascals. So what's this little element of soil experiencing? It's experiencing an increase in stress of, and we'll call it net foundation pressure. Remember, it already had 41 kPa acting on it, and we've stuck 80 on it. So the net foundation pressure equals 80 minus 41 equals 39 kilopascals. So that's the additional load. Alright, so we're going to work in the undrained condition. So that's short-term total stress, and that's going to give us the initial settlement. As soon as we load this thing up, this is the settlement that it's going to undergo. They've already calculated the stress dissipation with depth, change in sigma 1 or change in sigma v at the midpoint of this layer equals 0.7 by 39, which was the net pressure, which equals 27.3 kilopascals. And the change in sigma 3, because we're working in total stress, it's 0.3 by 39, which equals 11.7 kilopascals. That's stress dissipation with depth. We're going to talk a little bit more about that later. You should know that stress decreases as a function of depth, because in linear elastic behaviour, of what we're going to talk about later with Hooke's law. They've already calculated it for us, just to make it easy. Okay, so the next step we're at is we're going to start thinking about applying Hooke's law. Let me write it out for you first. Change in strain, ZZ, which is what we're interested in, the change in strain, so we can calculate settlement in the Z direction, vertically, equals the change in stress, ZZ, minus undrained Poisson's ratio times the strain in stress XX plus the change in stress YY, all divided by E. So really, all we're really doing here is elastic behaviour, and you know that in the linear part, let me draw it, stress, strain, and a stress strain curve like that. The modulus E just equals change in stress and change in strain. And that's all this Hooke's law is. The change in strain on the top line here, change in stress, and on the bottom is the modulus. Modulus equals change in stress on change in strain, therefore change in strain equals change in stress on modulus. So that is just exactly the same as that up here. Looks a little bit more complicated, and I'll try and explain what's going on with the top line of that equation. Alright, so there's a little soil element sitting somewhere. It has a vertical stress and two lateral stresses acting horizontally. Firstly, we're going to use this as a sign convention. So this pointing downward is positive, and that's positive. Easiest way to think of it is a sponge. I'm just going to work in 2 dimensions. But a sponge sitting on your bench, and there's a vertical stress, sigma 1, and a horizontal stress. I'll call it sigma 3 just because that's a convention we're going to use later. And you know that's just air pressure acting on your sponge. But it's really just sitting there quite happily, like that soil element above it is. It's been there for a long time. And it's a good model. That's positive, and that's positive. Okay, now let's think about that same soil element. If I apply a delta sigma 1, so I've increased the vertical stress, what's going to happen to this soil element? So let's go back to our sponge, sitting here on the bench. If I apply a delta sigma 1 there, just logically think about it, not in terms of soil mechanics or stress analysis, what's going to happen to that sponge? It's going to bulge out at the sides, isn't it? And essentially we're going to have a stress going laterally, which is a change in sigma 3 this way. And the same thing's going to happen to our stress element up here, change in sigma 3, and that way a change in sigma 3. Sorry, let's correct that before I get too excited. Change in sigma 2. So we're using the same terms in the 2 models. So what's going on here? This stress is behaving laterally sideways. So I'll notice over here in the first one, acting into the element was positive, so that's negative. And this one's negative. Just trying to get it clear in my head what I'm trying to say here simply. You should all know that Poisson's ratio is the ratio of vertical to horizontal stress or strain. So what we're going to do, these over here on the right hand diagram, these changes are some function of Poisson's ratio with regard to the vertical strain, or stress, sorry. Which brings us to Hooke's law, back up here, where I did this top layer of this equation. Let's just write the denominator out. It is a change in vertical stress. We'll call it sigma 1 for the time being. We're not going into rotation of these axes. Minus mu times sigma 3 plus sigma 2 is the top of that equation. So what's going on? Let's just scroll back up here. And this is the change in vertical stress, or sigma 1 equals that. That's the change in stress from here. The elastic modulus equation. So we can look at that now and say that the vertical stress that I've circled here on the right, minus, because they're acting in a negative direction on the right here, this ratio, Poisson's ratio, of sigma 3 plus sigma 2. I'll just highlight them in red, this one and this one. Really just sums up, and if you think about that, that's why stress decreases with depth, because this vertical stress is constantly being dissipated sideways through the action of Poisson's ratio. Hopefully that makes sense. And the only other thing I wanted to discuss was this, sigma 3 plus sigma 2. In our case, they're the same. They're exactly the same. So that can become the change in sigma 1 minus 2 times the Poisson ratio times sigma 3. 2 times sigma 3 is the same as the area in the brackets above it, and that's the equation we're going to use. It goes through a couple of steps in the tutorial, but really that's where it comes from. Okay, before I go any further, I do realise I stuffed up the numerator and denominator in that previous section, and while I'm no Spielberg, it takes a bit to do these things and you're thinking of 4 things at once, so I don't want to get 100 emails about that. Okay, so we know that the increase in vertical stress is the change in the sigma 1 minus 2 times Poisson's ratio times sigma 3. Just a little sidetrack there. You can see how if we rotate the principal stress, now that you know that, you can see it's not that elaborate in rotational principal stresses and resultant stresses. It's all just basic trigonometry. But I digress. Alright, and that equals the change in, I'm still working on that equation, the change in sigma 1 minus the change in sigma 3. If you remember, I'll make it a red pen. New here, the Poisson's ratio is 0.5. So 2 times 0.5 is 1. Hence we can simplify it down to that, which equals what we've calculated before, 27.3 minus 11.7 kPa, which equals 15.6 kilopascals. Get it right, Mark? .6 kPa. And then back to our modulus equals change in stress on change in strain. Making a lot of mistakes here. Change in strain goes to change in strain equals change in stress on the elastic modulus, which equals 15.6 that we just calculated, divided by the modulus, which was 12,000 given before. Remember, we're working in undrained total stress, so it's the undrained modulus, which equals 1.3 by 10 to the minus 3 strains. And if I want settlement, settlement goes to 1.3 by 10 to the minus 3 strains times, it's just a percentage, 12,000, which is the layer thickness. Apply that strain over that layer thickness, and that equals 15.6 millimeters. Later, just lock this away for later when we're doing some calculations. That's row I, initial settlement. Okay, all that preceding stuff was the undrained coat settlement. Worked on total stress, and it gives us that initial undrained settlement we've spoken about in the lectures. So now we're going to work on the drain case. The only difference here is we're going to use some drain parameters. Poisson ratio equals 0.25, and E prime, the modulus, equals 10 by 10 to the 3. Everything's exactly the same, apart from the change in vertical stress is the same, 27.3, but you will notice that there was another factor of 0.1 we multiply it by, so the change in horizontal stress equals 0.1, which we were given at the start, times 39, which equals 3.9 kPa change in horizontal stress. Going right back to our explanation of Hooke's law, everything's the same. So the change in vertical stress equals the change in sigma 1 minus, remember, because they're acting in the opposite direction, a half change in horizontal stress. I was just having a little think there, because remember back there we were doing 2 times mu, which equals 2 times 0.25, which equals 0.5. That's where this half comes from. Okay, equals the change in sigma 1 is 27.3 minus a half times 3.9, which equals 25.5 kilopascals. Slide up, therefore exactly the same as before. The change in the strain vertically equals 25, mistake, 25.35, 25.35 divided by 10 by 10 to the 3, which equals, that was just the strain, change in strain vertically divided by the effective modulus, and that all equals 2.535 by 10 to the minus 3 strains. Applying that over the 12 metres for the settlement equals 2.535 by 10 to the minus 3 times 12 metres, which was the layer thickness, which equals 30.4 millimetres. So that obviously there's more settlement. The drain condition implies that all the excess pore pressure is drained away. So we call that rho T for total settlement. We know the rho I from before, the initial settlement, was 15.6. So we can calculate rho C, consolidation, equals 30.4 minus 15.6, which equals 14.8 millimetres. So there's been 14.8 millimetres consolidation settlement after that initial 15.6 initial settlement. Now there's another type of settlement. What happens? If I can quickly draw a sketch here that hopefully somehow shows you a consolidation curve where that's 100% consolidation. So that's change in stress, and that's settlement, and 0%'s up here somewhere. Don't need to really worry about that. But after 100% consolidation, you'll see here that there is additional settlement occurs. So 100% is when all the excess pore pressure is drained away, and we get this additional settlement. They refer to as rho OD, the odometer settlement, and that's really, we also call it creep. So what's really happened is the pore pressure is drained away, but the particles are getting closer together, almost compacting, I suppose. And as they get closer together, we get some further settlement called creep or row odometer. And that's where this Skempton-Buren mu came in. Remember we were told at the start that mu equals 0.5. Skempton and Buren came up with this, and they tell us that row odometer equals consolidation settlement, which we just calculated up here, 14.8. 14.8 divided by their coefficient mu, which is 0.5. So this additional creep that's going to occur is 29.6 millimetres for row odometer. Okay, hopefully that explains week 5 tute. If you've got any questions, feel free to ask me in the lecture.